Okay, so today we are going to go over section 3.5. We're spending Monday, today, and Wednesday on it. Friday, we're going over the last section, and then next Monday is your review, and next Wednesday is exam number 2. Again, everybody has to be here for exam number 2, so make sure you are in class on Wednesday at 10 a.m. for exam number 2. I told you last time I was going to give you this sheet for note cards. If you're on Zoom, this is under week 8 documents. I put it up there this morning. And this is all the things you need to know for your exam, okay? This is all the things, none of this is given to you on your exam. So let's kind of go over all of these things so far, all the things we've learned so far. So the first thing is the vertex of a quadratic. Remember, you have two different forms. You have the textbook calls it general form and standard form. I called it vertex form on here. If it's in the form of a times x minus h squared plus k, your vertex is just x and k, not x, h and k. If it's in general form, the ax squared plus bx plus c, your vertex is negative b over 2a is the x value. The y value is plug in the x value into your function, work it out, and get out the y value. The axis of symmetry, if you're in vertex form, the axis of symmetry is just x equals h. If you're in general form, it's the negative b over 2a. Okay, and remember it's an equation, you have to have x equals that number. To tell if a quadratic opens up or down, if your a value is positive, it opens up and it has a minimum value. If your a value is negative, it opens down and has a maximum value. To find x-intercepts, you plug in 0 for y, solve for x, and you usually have to do that by factoring or using quadratic formula. To find the y-intercept, plug in 0 for x, solve for y. A polynomial is a function with exponents that are positive whole numbers. The degree is the exponent of term with highest exponent. So you're looking for the highest exponent in your equation, and that's the degree of the equation. Your leading coefficient is your coefficient in front of the highest degree term. In behavior, if your degree is even and your leading coefficient is positive, they both go up. If your degree is even and your leading coefficient is negative, they both go down. If your degree is odd, they're going to go opposite directions. If it's positive, it falls on the left, rises on the right. If your leading coefficient is negative, it rises on the left and falls on the right. Okay. Multiplicity, remember that's how many times you get an answer. If you have an even multiplicity, your graph touches the x-axis and turns. If you have an odd multiplicity, your graph just crosses through the x-axis. The maximum number of turns is 1 less than the degree, so degree minus 1. Remainder theorem says if you want to find f of c, divide your polynomial by that c value and your remainder is that answer. And this is the last thing we've gotten to so far. The rational zero theorem says the possible rational solutions are the p's divided by the q's. P is the factors of the constant, q is the factors of the leading coefficient. Okay, so that's a whole lot of information we've gone over so far. Today we are going to finish off, or we're going to do this part right here, the asymptotes, and then on Friday we'll do the inequalities. Okay, so today is section 3.5, which is graphing rational functions. I just remembered that I have a note sheet for this. Dang it. Well, too late now. We're going to do it on paper. I don't have it with me, sorry. So section 3.5 is graphing rational functions. You know what? Good thing we have 2 days on this. I'll get that next time. I'll print that out for next time. We're not gonna get through all of it anyways, it's fine. Okay, so first of all, let's talk about what a rational function actually is. So a rational function is just a quotient of 2 polynomial functions. Okay, so it's 2 polynomial functions divided by each other. So a rational function is just the quotient of polynomials. Okay, so for example, if I had f of x equals x squared plus 7x plus 9 divided by, I don't know, x cubed plus x minus 5. That's an example of a rational function. Okay, we've talked about these before. What have we talked about with rational functions? Why have they come up a few times in this class? You're right. Those are, okay, so you're using, it's not rational function. Those are rational solutions. Yes. She was saying the P and the Q is the possible rational solutions. That is totally true. We've seen these because the domain is restricted here. We've been finding the domain of this, right? So remember, we're not allowed to divide by 0, so your domain is restricted. And that comes into play huge when you're talking about rational functions, okay? So let's remind ourselves how to find the domain. Okay, so let's start off if I had the function f of x equals x squared minus 9 over x minus 3. Okay, so remember, domain is all the numbers you're allowed to plug in for x and get an answer. So in this case, we're not allowed to divide by 0, so I can't have a 0 on bottom. For this one, you can probably just tell what's the number we're not allowed to have here. 3, because when I plug in 3 on the bottom, I get 3 minus 3, which is 0. If you can't just look at it and tell, you can always set the bottom equal to 0 and solve, and you will get that answer every time. Okay. So this is the number I cannot have. My domain is every single x value except for 3. So I can write that a couple different ways. Interval notation, though, would be negative infinity to 3 union 3 to infinity. Look at this one. If I had f of x equals x over x squared minus 9. So I have to set the bottom equal to 0 again to find the domain. So x squared minus 9 equals 0. There's 2 ways you can solve this. How many answers should I have for this? 2, because my degree is 2, right? This is a quadratic, it should have 2 answers. You can solve using square roots, or you can factor. What do you want to do? Square roots. So you can add 9 to both sides. You get x squared equals 9. Take the square root. Just don't forget your plus or minus. So we get x equals plus or minus 3, which that's 2 answers there, right? Positive 3 or negative 3. So I have 2 places where my domain is restricted here. I can't have an x value of positive 3 or negative 3. So the way you would write your domain in interval notation here, it's kind of like the idea of at negative 3, I cannot have a number there. And at positive 3, I cannot have a number there, but I can have it anywhere else other than that. So you have to write 3 pieces for my interval notation. This first piece over here would be negative infinity to negative 3, not included. This middle piece would be from negative 3 to positive 3. Both of those not included. And this last piece would be positive 3 to infinity. So that's the domain. Questions about that? If you had 3 numbers as your answer here, you'd have like 4 pieces because there's three cuts in it. Okay, what about if it was the problem? G of x equals x plus 3 over x squared plus 9. So again, for your domain here, take the bottom, set it equal to 0 and solve. X squared plus 9 equals 0. If I solve the same way as I did last time, subtract 9 from both sides, I get x squared equals -9. So then we're going to take the square root of both sides. Don't forget your plus or minus. So I get x equals plus or minus, what's the square root of -9? 3i. So positive 3i and negative 3i. Okay, so I do technically have restrictions to my domain, but they're imaginary restrictions. So do you have any numbers that you can't have here? Any real numbers you can't have? No, there was only like imaginary numbers you can't have. So your domain here is -infinity to positive infinity. Okay, so let's talk about these restrictions on your graph. It doesn't mean that your graph is like, you know, it doesn't mean it just stops and then it starts back up over here. Like you have this like big opening right there. It looks a little bit different. So let's graph the parent function for rational functions. So the parent function is the one without any transformations on it. The parent function is f of x equals 1 divided by x. My domain is restricted here. What's the domain of this specific function right here? What number can I not have on the bottom? 0. So my domain is -infinity to 0, 0 to infinity. Okay, so when I graph it, I'm going to make a table of values here. I can't pick the number 0 here, because if I go to plug it in, it's not going to work, right? So let me pick -2, let me pick -1. Let's go ahead and pick -0.5 and -0.1. And you'll see why in a minute when I pick those numbers. And then I need to pick numbers bigger than 0 also. So I'm actually going to make another table of values. So I need to pick a number close to 0. Let's do 0.1, 0.5, 1, and 2. If you plugged in 0 here, do you know what your calculator would say? Error. Yeah, it'll literally say error on your table because you can't do it. Okay, so let's graph these or find these on the table of values. There's a couple different ways you can do it. What's one way you could find this table of values? Yes, you can use your calculator for it. Let me show you real fast how to do it by hand. You plug in your x values into your equation. What's 1 divided by -2? -1/2, right? 1 divided by -1 is -1. When you start getting into the decimals, it's a little bit more work. You might want to type it in your calculator. Or you could go to your graph and clear out whatever you have there and type in 1 divided by x. And then you can go to your table. For me, it's second graph to go to my table. And I have some of my numbers here. I don't have all the numbers I picked. Do you know how to change the table to where you can type in what numbers you want? If you go to, it says table set right here above window. If you go to table set, you can change independent is your x value, dependent is your y value. You can change your independent instead of automatically putting numbers in. You can make it ask what numbers you want to put in. And then at your table of values, it's blank here and you can type in whatever number you want. If you are going to math classes past this one, this would be very helpful for you. Okay, so if I type in -2, it tells me my answer is -1/2, -0.5. When I type in -1, it's just -1. And now I can type in my decimals, -0.5, I get -2. negative 0.1, I get negative 10. Positive 0.1, I get positive 10. Positive 0.5, I get 2. Positive 1, I get 1. Positive 2, I get 0.5. I'm going to go ahead and do 3 here. I get 0.33. Okay, and just a heads up, once you change it to this, it's going to keep your table values like this until you change it back. So 2 ways to change it back. You can literally go back to table set and make it go back to automatic, or your always safe option, if your graph always messes up, just clear your memory and it resets it back to the normal settings. So that's always it. Like if you're just can't figure out what's going on, just clear your memory and it's the easiest way to get it back to normal. Okay, so let's graph these on a graph. We're going to say this is -1. This is -2. Positive 1, positive 2. I went to positive 3. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so when I start plotting my points, -2, -0.5 is going to be about right here. At -1, we are at -1. It's going to be here. At -0.5, so that's in between 0 and -1 on your x-axis, we are at -2. At -0.1, so that's really, really close to 0 on the left-hand side of your y-axis, we are down at -10, so it's like right way down here. Okay, so that is one piece of your graph. It is like a, I don't know, upside down L shape. I don't know how to describe it. It is this piece of your graph right here. It looks like it's like a curve with your x-axis and your y-axis. Okay, the thing about this is it does not ever get to the x-axis or y-axis. It gets really, really close, but it never actually touches it. And that should make sense on the y-axis. Why is your graph never going to touch the y-axis? Because we have that we're not allowed to have 0, right? You can't plug in 0 and get an answer there. It says error. So it's going to get really, 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 really close to it, but it's never actually going to touch it. Okay, it does the same thing on the opposite side at 0.1. So it's like right here. We're all the way up at +10. At 0.5, we're at 2. At 1, we're at 1. At 2, we're at 0.5. At 3, we're at 0.3333. So same thing here, but it's like it's decreasing here. So it's like that. Okay, so this idea of getting really, really, really close here, these are called asymptotes. And that's what we're going to be spending a lot of our time with rational functions on, because that's what makes rational functions special. Asymptote is like an imaginary invisible line on your graph that your graph gets really, really close to. It approaches it, but it never actually touches it. Okay, so I actually have 2 asymptotes on this. Where would your asymptotes be on this specific graph? 0 on the x and 0 on the y. So essentially 0 on the x-axis is your y-axis, right? Let me get a darker or something. It's like I have a imaginary line right here that it gets really, really close to it and never touches. I also have a horizontal one right here that it gets really, really close to and never touches. Okay, so we are going to use mathematical language to describe these asymptotes. This is a big idea in like pre-cal and calculus. So if, again, this is your last math class and this doesn't make sense to you, like, don't worry too much about it. But we're just going to describe what our graph does on the end here, okay? So first of all, the graph does not exist at 0, at x equals 0. Does not exist at x equals 0. Okay, the next thing we're going to say is as x approaches 0 from the left. We're about to describe what our graph does. So we're talking about x values here. So look at your x values on your graph. So x values is all this right here, right? We can approach 0 two different ways. We can come at 0 this way, or we can come at 0 from this way. If we're coming at it from the left, what does your graph do? As I'm getting closer and closer getting closer and closer to 0, what is your purple graph doing? Going down, right? So as x approaches 0 from the left, the graph goes down. Okay, that is the words way to say that. Let's write it with mathematical notation because it's a lot faster. So the way we write it with mathematical notation is we say as x approaches 0, the way we say from the left is we put a little negative up here on the top right-hand corner of 0. So that means as x approaches 0 from the left, your graph, what do we call graphs? What's the name of this specific graph? F of x, that's the name of a graph, right? So f of x approaches, goes down. What is it approaching? Negative infinity, because it's going down forever. So that is mathematical notation of the sentence we just wrote. As x approaches 0 from the left, our function f of x approaches negative infinity because it goes down. Does that make sense? Okay, let's do the opposite direction. As x approaches 0 from the right, if we're coming up this way, getting closer and closer to 0 here, what's happening to our purple graph? It's going up, right? So as x approaches 0 from the right, our graph goes up. Okay, so mathematical notation for this is as x approaches, gets closer to 0 from the right. How do you think we're going to say 0 from the right? A plus. The reason why we put the minus and the plus is like this is on the negative side on the left-hand side. This is on the positive side, the plus. Even if this was like a 1 or a 2, negative means on the left, positive means on the right. And that should kind of make sense a little bit. So as x approaches 0 from the right, our function approaches what number? Infinity, because it is positive. It's going up. Okay, so we just described this invisible dotted red line here, which is called a vertical asymptote. Okay, so this is a vertical asymptote, asymptote. There are not enough vowels in that word. Okay, the next thing we are going to describe is the end behavior. So in behavior, on the ends of the graph, what is it doing? So we're going to describe this purple line right here on this side. As x goes to the left, right? So as we're going to the left, so we're going to do it with words and the mathematical notation. As x goes to the left, as we get further and further to the left, what is your purple line getting closer and closer to? Zero, which it's getting closer to like the y value of 0 now, right? As x gets to be a bigger negative number, that my y value is getting closer and closer to 0. Okay, so the graph gets closer to 0. So with mathematical notation, as x goes to the left, how am I going to say that? As x approaches what? Negative infinity, because going to the left is a bigger and bigger negative number. So as x approaches negative infinity, your graph approaches 0. And we don't have to put the plus and the minus like the left or right here because negative infinity is always to the left. Okay. On the other side, as x goes further to the right, what's your graph getting closer and closer to? 0. It's coming in from the top side this time, but it's still getting closer to 0. As x goes to the right, the graph gets closer to 0. So as x approaches, what number's further to the right? Infinity. F of x approaches 0 as well. Okay, this is the idea of limits, which you're spending like weeks and weeks on in Cal 1 at the very, very beginning of Calculus 1. Okay, what is this describing? We described this red line going this way on the x-axis. What do you think that's called? That's your horizontal asymptote. Okay, so we have 3 different types of asymptotes for rational functions. Every rational function is always going to have a vertical asymptote. The reason why every rational function is always going to have a vertical asymptote is because if I have something on bottom of a fraction, that's what makes it a rational function. And if it's on bottom, it makes a restriction in your domain, which is a vertical asymptote. Okay, so every graph that is a rational function will always have a vertical asymptote. Okay, so a vertical asymptote, we're just going to take a few notes on this, and then next time I'm going to give you a note sheet and we're going to go over it again. Asymptote. Okay, so the vertical asymptote, every graph's going to have it. It's going to be a vertical line on your graph. We usually do it a dotted line because it's not actually a part of your graph. It's just like a boundary that your graph approaches. Okay, so how do you think you find this vertical asymptote? Yeah.
Is it based on the vertex?
These don't really have a vertex. It's based on the domain, like we've already been doing it essentially. Like where your domain is restricted, that's your vertical asymptote, right? So the way you find the vertical asymptote is you set the bottom equal to 0. And solve it. So we've been doing this already. We did that at the beginning class when we found the domain. Give me a second to write that down and then I'll show you. So like that first problem we did, the vertical asymptote here is 3 because I don't have, my domain is restricted at 3. For number 2, my vertical asymptote was +3, -3. Okay, for number 3, we didn't have a vertical asymptote. That was just a weird problem, but I wanted to show you kind of what happens with the weird problems. For this one, the parent function, the vertical asymptote is 0. When you set the bottom equal to 0 and solve, you just have x equals 0. Okay, so your vertical asymptote is always the restriction on your domain. You just set the denominator equal to 0 and solve. Okay, so horizontal asymptotes. These are the ones that are a little bit more difficult and take a little bit of time to figure them out. Okay, so the horizontal asymptotes, you have 3 options here. There are 3 different situations you can have, and depending on the situation, your asymptote is different for each situation. So I have a mnemonic that I did not make up. My teacher taught this to me when I was in high school, and this is what I've always used. There was a story she went along with it. I don't remember the story, so it means nothing at this point other than just a bunch of letters. And it is BOBO, B-O-B-O, and I'll explain what all this means in a minute. Botn, which is B-O-T-N. Eats DC. It was some story about a clown, but I don't remember any of it at this point. So, okay, so what we are looking at when we use this mnemonic is the degree on top and the degree on bottom. So you're looking at the degree on the top and the degree on the bottom of your polynomial function. The polynomial on top and the polynomial on bottom. Okay, if your degree, if you look at the first part, is bigger on bottom, that's what the B-O-B. If it is bigger on bottom, the O tells you your answer. Your horizontal asymptote is y equals 0. So that's the B, O, B, and the y equals 0 is the second O. Okay. The next part, what do you think this means? Bigger on top. B-O-T is bigger on top. And the N stands for none. There is not a horizontal asymptote. So B-O-T, N is the none. Okay, so I said we had 3 options. One option is bigger on bottom. One option is bigger on top. What's the third option? They're equal, right? If it's not bigger on top or bigger on bottom. That's the eats part. Its exponents are the same. Okay, so this is exponents are the same. That's the eats part. The DC tells you what your answer is. It's y equals, you divide your leading coefficients. So divide coefficients is what the DC stands for. So exponent is y equals, I'm just going to write divide coefficients, and then I'm going to explain it some more underneath it. Divide coefficients. So that's the D and the C. I guess it's actually leading coefficients. Okay, so do you see what all these letters stand for? Okay, it's a lot of writing for not that long of a process, essentially. Okay, so let me give you a few problems and we'll see which category it falls in. Okay, so number 1, if we had f of x equals x squared minus 2x plus 5 over x plus 3. What is the degree on top here? 2. right? Because your highest exponent on top is 2. What's your degree on bottom? 1, because your highest exponent is on bottom is 1. Is this bigger on top, bigger on bottom, or the degrees are the same? Bigger on top. What's your answer? None. There is not a horizontal asymptote here. Does that make sense? That's your horizontal asymptote is none. What would your vertical asymptote be here? Set the bottom equal to 0 and solve, right? So I'm gonna go ahead and do that one also. The vertical asymptote is set the bottom equal to 0, x plus 3 equals 0, subtract 3, x equals -3. That's your vertical asymptote. So we've done a lot of talking and a lot of writing for something that's not that hard to actually do, okay? Second problem, what about if it was x plus 3 over x squared let me make this actually work, minus 6x plus 5. Okay, so the degree on top here is 1, the degree on bottom is 2. In this case, is it bigger on top or bigger on bottom? This is the bigger on bottom, the bobo part. So what's your answer? Y equals 0. Horizontal asymptotes are always y equals a number. So y equals 0. This is the bigger on top, none. Okay, let's go ahead and do the vertical asymptote for this one. This one's a little bit more difficult. How do we do a vertical asymptote here? Set the bottom equal to 0 and solve. X squared minus 6x plus 5 equals 0. I have to factor that. What does that factor into? X minus 5, x minus 1. When I set both of those equal to 0, what are my two vertical asymptotes? Positive 5 and positive 1. So that's for vertical asymptotes. Okay, so we did bobo, we did bot, and let's do an eats DC now. So a situation for that one would be if I had the problem f of x equals 2x plus 5 over x minus 2. What's the degree on top? 1. What's the degree on bottom? 1. Do they have the same degree? Yes, because the highest exponent is the same here. So my horizontal asymptote is y equals, you divide your leading coefficients. What's my leading coefficient on top? 2. What's my leading coefficient on bottom? 1. So my horizontal asymptote is y equals 2. And this is the eats DC. Questions about that? Pretty straightforward, right? I think if you understand, if you don't understand this, this is a lot of information, right? Okay, so we are going to stop there today. If you'll go back and look at your little note card thing, we covered everything except for the slant asymptote here. So the vertical, set the bottom equal to 0 and solve. Horizontal is bobo, bot, and eats DC. Look at the degree on top and explains all that. And we'll talk about slant next time. Next time I will have a packet of notes for us to do together. Okay, so make sure you're working on your homework. Next time I'll also have the review for your exam next week for you to start working on. So let me know if you have any questions, and I will see y'all on Wednesday.